Okay, so for the second half of 10.5, we cover planes. Now, a plane in 3 dimensions is described by a vector perpendicular to the plane or orthogonal to the plane. And we'll denote that as the vector n. It's called the normal vector. And also a vector within the plane will help to describe the plane. So we see it in a picture here. The normal vector is perpendicular to the plane. If we know a vector within the plane, then we can fully establish the equation of the plane. So r minus r naught is a vector in the plane. What will typically be the case is that r will be the vector x, y, z, our variables. R naught will be some vector whose terminal point is in the plane. So, in fact, actually r naught is here because the difference r minus r naught points at r. Anyway, r minus r naught will suffice for our equations of planes. Okay, so what we know about two vectors that are perpendicular to each other is that their dot product is 0. So this establishes the basis for our equation of a plane, and it gives us a first equation to start with. Okay, so n dot r minus n dot r naught equals 0. Remember that r will have variables x, y, z. N will be a vector that's known or found within a problem, and so it will be numerical values. N is, again, same vectors known with numerical values, and r naught will have some numerical values. So ultimately we'll have something like ABC, which is our normal vector. You can think of it as the direction vector, kind of, or analogous to that at least. X naught, y naught, z naught is r naught, and this vector n dotted with the variable x minus x naught, and then likewise for the other components will be 0. Multiply that through. That's the finished dot product right there. We could simplify it even further, and we'll see that in the example that we do and in later problems. So that's the basis of a vector in, or a plane's equation in 3 dimensions. Okay, so find an equation of the plane through the point 5, 3, 5, and with normal 2i plus j plus or minus k. So we basically have all the parts we need to get started right here. So we'll vectorize our point 5, 3, 5, because we know that this point needs to be on the plane. So we call it r naught. R, so any points x, y, z that are going to be on this plane should satisfy the condition that x minus 5, y minus 3, and z minus 5, which forms this vector r minus r naught, must be perpendicular to the normal vector here. And by that perpendicularity means their dot product must be 0. So that's what establishes and explains more or less why we set this up the way we do. Okay, so you always kind of have to think about the geometry. These problems get a little bit tricky and they're a little bit like puzzles often. So carrying out the rest of this is pretty straightforward though. 2 times x minus 5 gives us this expression. 1 times y minus 3 is here. Negative 1 times z minus 5 changes the signs in that expression, all equal to 0. It's very common to collect all the variables with their coefficients on the left, and on the right hand side combine all the constants, and that's how we'll arrive at the answer that we see down at the bottom boxed. So this is a pretty standard form for the equation of a plane. In fact, it is the standard form for the equation of a plane. So it's an easy start. These things, of course, can be a little bit challenging if we're given different information and asked to find the equation of a plane. Here's that standard form I mentioned. Okay, so that's the scalar form, I guess, is another way of saying that, versus the vector form, which we saw on the previous page. Now let's do a problem that requires a little bit more thinking. So we're asked to find the equation of a plane passing through the origin and the 2 points 2, negative 4, 6, 5, 1, and 3. So we're given 3 points, and we need the plane to contain all 3 of those points. Well, similar to a line, 2 points will determine a line in space or in 2 dimensions. Okay? Now, 3 points will determine a plane. So imagine 2 points have already determined a line, and you put a 3rd point anywhere in space. If all of those points have to be on the same surface, that will fully determine a plane. Okay? So let's get to work on this. The first thing we need to do, so the overall strategy, I'll say this. We need to start with forming two vectors that live within that plane. So if we form any two vectors between these 3 points that we're given, then we'll have two vectors that are within the plane. It's maybe convenient, easy to visualize. If we choose a common initial point for those two vectors, then we'll form something that looks like, just to sketch it, like this. We use a common initial point and form the vectors from those 3 points. Now we've got two vectors. They're in the plane. Okay? That only gets us so far because what we need ultimately is a normal vector. And I'll sketch a normal vector, something like this. And it's going to need to be perpendicular to both of these vectors since it is normal to the plane that they're in. Well, how do we calculate, how do we find a normal vector to two vectors? Well, if we know that this is the vector A and this is the vector B, we have them fully determined, this vector right here can be calculated as the cross product. So here our cross product comes in to save the day. And that's the strategy in this problem. We have 3 points. Those 3 points I'll represent just to make sure we've seen that. This would be the end of one of the terminal side of one of the vectors, a common initial point, and a terminal initial point. It really, again, doesn't really matter if we make them have common initial points. It's just convenient to view it this way, and it could help your workflow as well. So in our problem, the origin is one of the points. So what better common initial point to have than the origin? So we're down here forming the vector A and the vector B. Okay. To form the vector A, we'll take the point 2, negative 4, 6, and we'll subtract the origin from it. 2 minus 0, negative 4 minus 0, 6 minus 0, we end up with this. And then we see, okay, that's going to be easy. Similar calculation for B gives us, the vector B gives us 5, 1, 3, very similar to the point we were given. Okay, if the third point wasn't the origin, or if no points were the origin, then we'd have to do a little, we'd see a little bit more of a change in what these vectors actually are. So, next step, like we explained, take the cross product of A and B, using the determinant of this setup right here with I, J, K, standard basis vectors at the bottom. Once that's calculated, we end up with, we'll call this vector the normal vector N. In this case, in vector form, we got negative 18, 24, 22. Now that we know the normal vector, all we need to do is use that normal vector in any one of the points that's on our plane to form the equation. It's a really nice option to have. We just go directly to one of these points, and we're going to use the origin because, well, what better point to plug in than a bunch of zeros with this N vector? So we'll have, and the way we use the point, so you might ask, why aren't we using another vector in the plane? Well, that's what we're forming right here. X, Y, Z is an arbitrary point in the plane, so it's got to satisfy the equation of the plane in order to be a point on the plane. So x minus 0, y minus 0, and z minus 0 are the vectors that we're trying to create within the plane. They're just based off of the point 0, 0, 0. And when they dot any of those we dot any of those vectors with negative 18, 24, 22, the normal, we better be equal to 0. And that's essentially how we're forming this equation. And when we're done, we cancel out common factors of 2 and set all the variables on the left and the 0 on the right. And we've got our scalar equation for the plane. So again, this is our maybe vector equation of the plane. This is the scalar equation. It's most common to use this one. Okay, so one last calculation we can look at is the distance from a point x1, y1, z1 to a plane. ax plus by plus cz plus d equals 0, given that we know both of those pieces of information or can establish them. All right, this formula is a little bit complicated to calculate, but it uses the scalar projection formulas in order to work. An interested student could check the proof out in the textbook. We'll leave this here for now. And let's just look at the example. That's really the more important part of what you'll be accountable for in terms of the material, how to use this formula. So we're asked to find the distance between the given parallel planes. So they at least tell us the planes are parallel. We could check that the planes are parallel by seeing that their normal vectors are parallel to each other. And remember, a good check to see whether or not two vectors are parallel to each other is to take their cross product and set it equal to 0, or see if it's 0. If it's 0, then they're parallel to each other. If not, then they're not. Another way to see if two vectors are parallel is just to see whether or not they're just a scalar multiple apart. Okay. Anyway, we're told that, so we don't need to worry about it in this specific problem. So this vector here, or this equation for a plane here, is really interesting to me. It doesn't have a constant in it. So what does that mean? It means that it satisfies, or the point 0, 0, 0 satisfies this equation. You plug in 0 for z, 0 for y, 0 for x, and both sides will be 0 equals 0. So that means the origin is on this plane. That's fantastic. We can use that piece of information as a point on this plane, and we'll find the distance between that point to this plane. So perfect. And that's more or less what we're described down here. So we do the work to figure out, we'll set x and y equal to 0 to make our life as easy as possible. Most of the time, z won't be 0 in general. In this case, we already determined that it will be 0. But this will be your general workflow here. So make things easy on yourself. Set two variables equal to 0, and then find a third one, or what the value of the third one is, and that'll keep it kind of easy to find the distance between a point on this plane and then the other plane. So we've concluded that one of two ways the origin is in this plane. Now we can use the distance formula. We have a point. It'll be the origin. Oops. This will be the origin's values in the formula, or where we plug them in. And now we also have the plane, so we know all the information we've got here. So we need to put the second plane into this form, and that's just a matter of rearranging some terms, but we end up with this expression as ax plus by plus cz plus d equals 0. And once we're there, we'll do 3 times 0 minus 6 times 0 plus 9 times 0. 3 times 0, negative 6 times 0, 9 times 0. All the zeros being the points, being the components of our point 0, 0, 0. And minus 1 is just d, or plus d, which was negative 1. Then we divide by a, b, and c, each of those squared, added up with a square root. And we have 1 over 9 plus 36 plus 81, square root of all that. And simplifying that, we get 1 over 3 root 14. And that's our final answer. I wouldn't worry about rationalizing denominators unless WebAssign or some other assessment asked us to do so. This is completely sufficient as is. So that's equations of a plane, finding the equation of a plane given some information, and finding the distance between a point and a plane, or two parallel planes, or possibly a line parallel to a plane, so on and so forth. So practice these problems, and good luck.